When you're driving in your car and you stop abruptly for any particular reason, you are experiencing a higher order derivative. In this case, this is the jerk. In objective 3, we're going to be able to find higher order derivatives. What does that mean? Well, we can take a derivative, and that derivative as a function represents the slope at every single point on that original graph. It's a function, so can't we take the derivative of that function? That's exactly what we're talking about. It's like finding the slope of the slope. Okay, so on example 12, let f of x equal x squared plus 3x minus 5. Find the instantaneous rate of change at x equals a. All right, so this is going to give us the slope at some generic point a on that graph of that parabola. And then what is the rate of change of the instantaneous rate of change? Once again, what's the slope of the slope function? Let's see. So, of course, the way we find the instantaneous rate of change at a is we got to take the derivative. We take f prime of a is equal to, and it will be a limit as h goes to 0, and then set it up like this. I want it at a, so it's at a plus h minus f of a all over h. And now I just plug this stuff, of course, into my function here. I would have a plus h squared. Is that plus 3? Plus 3 x plus, not x, are you kidding me? A plus h minus 5, and then subtract out a plugged into the function there. So it's going to change those x's to a squared plus 3a, and then minus 5. Over h. Okay, we know this would give us 0 over 0. We got to fix it. We're going to get rid of our parentheses here with our eraser tool, distribute the negative sign through that. Let's see, that's going to make this plus sign a minus sign, and this minus a plus, which is nice because, well, at least, I can see very clearly that the 5's cancel. Other stuff's going to cancel. I've got a feeling. Limit as h goes to 0. Got to expand out this binomial, a squared plus 2ah plus h squared. And then distribute the 3 plus 3a plus 3h minus a squared minus 3a. And then once again, cancel, 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 cancel. And maybe just go ahead and, for clarity, rewrite this. Limit as h goes to 0, 2ah plus h squared plus 3h, that looks like it, over h. And notice that everything across the top has a common factor of h, which I can factor out. Limit as h goes to 0, h times 2a plus h plus 3 over h. h's cancel. And I have, rewriting one more time, the limit as h goes to 0 of 2a plus h plus 3, and when h is going to 0, well, this whole thing is approaching 2a plus 3. And we found the derivative at some generic point 2a plus 3. All right, now this is always changing. It's a line, so depending on what value we stick in for our a here, it's always changing. So I want to know, at what rate is that slope changing? In other words, what is the second derivative at a? Now, I could use that limit definition, but it would be overkill because we have a line and we know the slope of the line is 2. So what we just found here is a higher order derivative. It's a second derivative. It's the derivative of the derivative. If the first derivative gives us the slope at any particular point, it's a pretty interesting question to ask yourself, well, what does the derivative of that slope equation give you? That will be a secret that's revealed in a future lesson. But let's take a look at the graph of this original one. There's the parabola. I graph the derivative. It's a line. And then I take the derivative of the green graph, and that one's just the constant number 2. Well, one way to think of this is Let's say that this is the position equation of some sort of particle. When I take the derivative of the position equation, I'm going to get the velocity equation. And then I can take the derivative of the velocity equation and I can get the acceleration function. That's an example of some higher order derivatives. And that's what's going on right here. This is a second derivative. It gives the slope of the derivative at each x value, and an application of that is the concavity. Okay, so I lied to you. The secret's revealed. It tells us something about how this shape is actually bent. We will talk about specifically what concavity means in another chapter, in another lesson. And then a physics application is the acceleration of an object. It is how fast the velocity is changing, which is an example of a second derivative.